This is Module 13, Lesson 6. It's our last lesson of this module. The one last thing that we need to look at is properties of solutions. Now, the specific properties that we're going to look at today are called colligative properties. So to get us started, right here you have an explanation of colligative properties. What this tells us is that when you make a solution, the properties of the solution are different from the things that made it up. And basically, your definition of a colligative property right here is, it's the properties of solution that depend upon how many particles go into the solution. You have 3 of those. They're listed right here. We're going to look at each one of them individually during the following slides. So you can pause this a minute and make sure that you have the definition of colligative properties and you know what they are before moving on. So the first colligative property, let's look at it. It's vapor pressure lowering. And quite simply stated, it says right here, solutions have lower vapor pressure than a pure solvent. That means that if you have a container of water up here at the surface of the water, if this is the water level, you're going to have tiny droplets of water entering into the gaseous phase, and that's making the vapor pressure. Well, what this is saying is that if you have a solution, like if we make it salt water instead of just water, you will have fewer droplets of water forming at the surface. Why is this? And it says it's because solutions, the water molecules are attached to something else. They're attached to the solute. Remember when we talked about dissolving or dissolution, solvation, how dissolving takes place is that the water molecules are now attached to what is in the water. So I think of it kind of like strapping an ankle weight to the water molecules. It makes them heavier. It makes it harder for them to go up here to the surface and then enter into the gaseous phase. So what this does is it lowers the vapor pressure. Now, this statement right here says that the decrease in vapor pressure is proportional to the number of particles of solute in the solution. Say what? Well, quite simply put, the more pieces that the solute breaks into, the greater the effect on vapor pressure. We practiced this in previous lessons. To give you some examples right here, if we had NaCl, we wrote that this would break up into Na pluses and Cl minuses. It breaks up into 2 pieces, the Na positives and the Cl negatives. So what if we had something different? What if we had something like MgCl2? What does that break up into? It breaks up into an Mg, 2 plus, and 2 Cl minuses. So this one breaks up into 3 pieces. So if this one breaks up into 3 pieces and this one breaks up into 2, MgCl2 is going to do the most damage to the vapor pressure lowering because it's 3 ankle weights instead of 2 ankle weights. What if we had something like sugar? Like this is glucose. So what if glucose went into solution? Well, it stays together. It's an ionic compound. It doesn't break up into pieces. So this would have the least effect on vapor pressure out of the 3 things that have been listed here. You have this one, MgCl2, and NaCl. So, basically, it's telling you below that ionic solutes that dissociate have a greater effect on vapor pressure. Well, to look at the ones that we have right here, we have 2 that change color. We have 2 that are ionic, NaCl and MgCl2. They have more effect because they break up into more pieces. And the more pieces they break into, obviously, the more effect that they have. Things that don't dissociate, like glucose or covalent compounds, they have less effect because, well, they stay together. If you didn't watch Tyler DeWitt's video during, I think it was lesson 1, then I would highly recommend that you go back and watch his video on dissolving in order to have a visual of how this actually takes place within the water. The next thing that we're going to look at is freezing point depression. What freezing point depression means is that basically the freezing point of a solution goes down. Now, how do you know this from everyday life? Well, you know that in the wintertime they put salt on the roads. And the reason that they put salt on the roads is because it lowers the freezing point of the water that's on the road. So instead of freezing at 32 degrees Fahrenheit or 0 degrees Celsius, it'll now freeze lower than that. And depending upon what salt they use will depend upon exactly how low the freezing point will go. Like we just said in the previous slide, if we used NaCl, that only breaks up into 2 pieces. So oftentimes when they salt the roads, they'll use calcium chloride because it breaks up into 3 pieces, which means it'll have a greater effect on the freezing point depression than NaCl. So why does this happen? Well, you should know from before when we talked about solids that whenever water freezes, it gets in a very orderly arrangement. It makes a honeycomb pattern, which is a nice crystalline arrangement, very orderly, very repetitive. And the solute particles, like these, get in the way of that happening. I think of it mentally in my mind like having a bunch of dogs running around your feet when you're trying to line yourself up in the middle of a classroom with a bunch of people. Like they get in the way. You can still line yourself up with other people and make a pattern, but it takes you more work and more time because of all the little critters running around at your ankles. So if you can think of it this way for the solute, the same thing is happening here. So what that means is that more kinetic energy must leave the solution in order to freeze it, so you have to make it colder. Now for the roads, there is a limit. Water will still freeze, so it's just lower, like maybe 20 degrees Fahrenheit or 18 degrees Fahrenheit, somewhere like that. So if we got down to like 3 degrees Fahrenheit, well, the water's going to freeze anyway, but at least it took it longer. You had a greater ability to drive in that time. Now, yet again, the amount of freezing point depression is proportional to the number of solid particles. So what that simply means is more pieces means greater freezing point lowering. So it's the same theme as the one before. Now we have one more to look at. We have boiling point elevation. So simply put, what this means is that the boiling point of a solution is higher than the solvent by itself. So remember from before that we said that this is in module maybe 12, that boiling point happens when the vapor pressure equals the external pressure. Well, we already said that vapor pressure is lower in a solution. So if you lower the vapor pressure with a solute present, then that makes it harder to reach the boiling point. You're going to have to put more energy in it in order to reach the boiling point. So this is true at your house. You've been taught most likely that if you have a pot of boiling water, that you should salt it to boil pasta. Well, the reason that you add salt to it, some people I've heard say that it cooks the pasta faster. Well, it may actually cook the pasta faster because what it's going to do is it's going to boil at a higher temperature. So, for example, instead of boiling at 100 degrees Celsius, it might now boil at like 105. So it'll take it longer to reach boiling, but once it gets there, it will boil at a higher temperature. So technically, you should be able to cook the pasta faster. And yet again, this is proportional to the number of particles. So, depending upon whether you have 1 particle, 2 particles, or however many, the more particles, the more you change the boiling point. So now it's practice time. You have a practice page that just simply tests your understanding of these concepts. Make sure that you have a little practice with it before a quiz. If you need me, ask during office hours.